Maybe the best way to begin a discussion of expected value is just to jump straight into a problem where it would come up naturally. So let's do that. This problem says the value of items along with the probabilities that they will be stolen over the next year are shown. What can the insurance company expect to pay in claims on your policy? That's the first question. Second question, is $100 a fair premium for this policy? Now, how would you go about answering such a question or such a set of questions? For example, looking at the first line in the table, the $2,000 laptop has a probability of 0.02, in other words, 2% chance of being stolen. So you have to balance off the value of the item with its probability of being stolen. This is the idea that we're exploring here. On average, the company will pay out $2,000 due to a stolen computer 2% of the time, according to this table. We can quantify this idea by saying that by insuring this computer, the company has an expected payout of $2,000 times 2%, or 0.02, which is $40. So let's actually add an expected payout column to our table and then calculate the expected payout for all of these items listed. We've already done the one for the laptop. It's simply the probability of it being stolen times the value of the item. So the iPhone has a $400 value and a 3% chance of being stolen, so it's 0.03 times 400, which is $12. That would be the expected payout for the iPhone. The Trail bike is a $600 value with a 1% chance of being stolen, so that would be 0.01 times 600, or a $6 expected value, expected payout. And the textbooks have an $800 value with a 4% probability of being stolen, so that would be 0.04 times 800, which is $32. Now if we add up all these expected payouts, we'll get $90. Now based on that, does a $100 premium seem to be fair for that policy? In other words, the company is not going to do it if they expect to lose money or even break even. They need to make a profit, so it seems to me that $10 profit would be fair. All in all, a $10 markup on a $90 expected payout, that's about 11%. That seems fair enough. Now let's look a little more closely at how we got that, because we're going to generalize it. We jumped right into an example to sort of motivate us for what we're doing, but now let's analyze what we did so that we can generalize. The first thing we did was take the probability of an item being stolen and multiply it by its cost. So we went to the computer first, then we did the same thing for the iPhone, then the same thing for the bike, and finally the same thing for the textbooks. And then we took those products, we took those 1, 2, 3, 4 products and added them up to get the expected payout of the company. This process leads us to the general definition. If an experiment has numerical outcomes, we'll call them x sub 1 through x sub n. With corresponding probabilities, we'll call them p sub 1 through p sub n. Then the expected value of the experiment is given by multiplying each outcome by its corresponding probability and then taking the sum of all those products. That's just what we did in the example we did earlier. Let's look at another simple example. This problem says to the right of the probabilities and values associated with 5 outcomes of an experiment. We're just calling them A through E, but there are 5 outcomes, and each outcome has a certain probability of occurring, and each outcome has a certain numerical value. Remember, by definition, if an experiment has numerical outcomes, call them x sub 1 through x sub n. In this case, it would be x sub 1 through x sub 5. With corresponding probabilities, that would be p sub 1 through p sub 5. Then the expected value is simply the sum of those products. So if you think of the values as x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, and then the corresponding probabilities p sub 1, p sub 2, p sub 3, p sub 4, and p sub 5, we can calculate the expected value very easily. We simply take the products and then add them. The easiest way to do that if you already have a table especially, is to make a column especially for that. So I'm going to add a probability times value column, and that's where I'll do my products. So for A, I take 0.1 times 5, that comes out to be 0.5. I'll take 0.2 times 5, that comes out to be 1. Then I'll take 0.2 times negative 2, that comes out to be negative 0.4. I'll take 0.2 times 2, which comes out to be negative 0.4. And finally, I'll take 0.3 times 9, which comes out to be 2.7. And according to my definition, once I get the products, all I need to do is sum them up. So if you add all 5 of those numbers, you'll end up with 3.4. So 3.4 is the expected value of this experiment. So when you're given explicitly the values and their probabilities, calculating the expected value is very straightforward. Let's look at another example. How many tails can we expect when we flip 4 fair coins? This is the first example we've looked at where we don't have the information in a table. But by the time we finish analyzing it, we will, because that's our goal here. Once we get the table values, we'll be able to do the products and then the sum of the products and get the expected value. I would always think when I'm doing 4 coin flipping of a tree diagram, that's probably the best way to envision the sample space. So if I'm flipping a coin on the first flip, I can get either a head or a tail, and then on each succeeding flip, no matter whether I start off with a head or a tail, I can get a head or a tail, and that propagates all the way down. The third toss, either a head or a tail, all the way across. And then of course the fourth is the same. So I end up with the possibilities H, 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 T, H, H, T, H, and so on until we finally get the very last possibility, which would be T, 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 T. And if you list them all, there will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there will be 16 items in the sample space for an experiment of flipping 4 fair coins. We've done this before. But what we're trying to do is see how many tails we can get. You can look at the tree diagram and see that it is possible to get no tails, but there's only one way, and that's if they're all heads. So there's one way to get no tails. I did put this here just in case you want to calculate without drawing the tree diagram. You can also calculate that by thinking of it as a combination of 4 things. Those are the 4 flips or the 4 coins, getting 0 tails. So you can get the 1 by doing the tree diagram and just looking and seeing there's only one possibility with no tails, or you can calculate it as a combination. It's your choice. You could also get 1 tail, but there's more ways than one to do that. The ways of getting just 1 tail, you could get head, 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 tail, that'd be this one. You could get head, head, tail, head, that'd be this one. You could get head, tail, head, head, and there's actually just one more. There's tail, head, head, head. Head. That's that one. So you can look through there and you can see that there are 4 of them. 1, 2, 3, 4, where you get exactly 1 tail. So there are 4 ways to get 1 tail. Again, the tree diagram will give it to you, or you can calculate it simply as a combination. 4 coins looking for 1 tail. Then of course there's a possibility that if you flip the coin 4 times, you'll get 2 tails. Well, how many ways are those? I'm not going through the tree diagram again and getting every one of them because it's getting messy enough already. but there are going to be 1, 2, 3, 4, 5, 6 of them. So there are 6 ways to get 2 tails. If you don't want to draw the tree diagram and search through, you can also calculate it as a combination. 4 coins looking for 2 tails. Either way you do it, you come up with 6 possibilities, 6 ways of flipping the coin 4 times and getting exactly 2 tails. Then of course you could get 3 tails. I'm going to stop searching through the tree diagram, but you can do that. You see where I have it highlighted. Or you could calculate it as a combination. You're doing 4 coins and you're looking for 3 tails. Either way you look at it, there are 4 ways to get 3 tails. There they are, 1, 2, 3, 4. And finally, you could possibly get all 4 tails. And there's only one way to do that, and that's tail, 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 tail. And you can get that as a combination, 4 coins, getting 4 tails, and that comes out to 1. So any way you look at it, whether you're doing it directly through the tree diagram or whether you're doing it by calculating the combinations, you should be able to get the number of ways to do each possibility. And like we said, there are 16 of them. You can double check. If you just go the combination route, you can add those up and see that there really are 16, and that corresponds to the 16 branches if you did a tree diagram. Notice I did a tree diagram in the very beginning, but if I'd really thought about it, I could have not bothered to draw the tree diagram and just gone straight to doing the combinations. It's totally up to you. In any case, let's put that information in a table now. Remember, to do our expected values, we need a table with the values and their probabilities. Well, what we're looking for here are the number of tails, so you need a column for how many tails you could get. Well, remember, if you're flipping the coin 4 times or flipping 4 coins, you could get no tails, 1 tail, 2 tails, 3 tails, or 4 tails. Now what's the probability of that? This is why we did the number of ways, so we could calculate the probability. We only wanted to know the number of ways to do this so that we could use that information to calculate these probabilities. We didn't do it just for the fun of it. What are the probabilities? Well, if you're looking for no tails, there's one way to do it out of 16. Remember, there's 16 different ways. So the probability of flipping 4 coins and getting no tails is 1 out of 16. What about getting 1 tail? Well, there are 4 ways to get 1 tail out of 16 possibilities, so there's a probability of 4/16 of flipping a coin 4 times or flipping 4 different coins, it's all the same, and getting exactly 1 tail. What about 2? Once you see what's going on, it's very easy. There are 6 ways to get 2 tails out of 16 possibilities, so there's a probability of 6/16 of getting 2 tails when you're flipping 4 pair of coins. 3, same idea. There are 4 ways to do that out of 16 possible, so that's 4/16. And then 4 tails, there's only one way to do that out of 16 possibilities, so that probability is 1/16. We've got it exactly where we want it now. Remember, when we're doing these expected values, if we can get it into a table with the values and their probabilities making up the rows, then all we have to do is multiply across and add. So now I just say, well, what is 0 times 1/16? I want to make that product. That's 0. Then I want to take 1 and multiply it by 4/16. That's just 4/16. Then I want to take 2 and multiply it by 6/16, which comes out to be 12/16. Then I take 3 and multiply it by 4/16, and that comes out to be 12/16. Finally, I take 4 times 1/16, and that comes out to be 4/16. And now that I have all my products, I just add them up. And that's the reason I didn't reduce any of the fractions. I know that if I'm adding fractions, I need a common denominator, so just ignoring the 0, which doesn't really matter, doesn't add anything to the sum. Everything else is 16, so I can just add the numerators. 4 plus 12 plus 12 plus 4 is 32. So I get 32 over 16, which happens to come out to be an even 2. So the expected number of tails, if you flip a coin 4 times or flip 4 separate coins, it's all the same, is 2. In this example, we're betting $1 on a single number of a 38 number roulette wheel. So the roulette wheel has, you spin it and it has numbers 1 through 38. If you win your bet, you get $35 and they give you your dollar bet back. If you don't win, you lose the dollar bet. So you bet $1, you pick a single number, the roulette wheel is spun. If it lands on the number you selected, you get your dollar bet back and a payment of $35. If your number does not come up, you lose the dollar you bet. The question is, what is the expected value of this bet rounded to the nearest cent? Again, your goal is to get a table with the values and their probabilities. Once you get to that point, you have it made. So you got to think about this. If you're betting on a single number out of 38 possible numbers, then you've got a probability of 1/38 of winning that $35. So if you're building a table, there are really only two things that can happen. You either win or lose. If you win the $35. Remember, the dollar bet got given back to you. So you had $1, they gave it back. So that just cancels out. So you end up $35 richer than you were if you win. And the probability of that happening is 1/38. But you're more likely to lose. But that is the only other possibility. You either win or lose. If the probability of winning is 1/38, that means the probability of losing is 1 minus 1/38, which is 37/38. So the probability of losing is 37 out of 38, but you lose only what you bet, which is the dollar. And the negative sign indicates that it's a loss. You lost that dollar with a probability of 37 out of 38. And that's it. You've got the table now, so really game over. You've got to multiply the probabilities and the values together and then add those results. So $35 times 1/38 is 35 divided by $38. We're going to do the same thing on the bottom, but remember that's a loss, so it's negative. So negative $1 times 37/38 is negative 37 over $38. And then it says to round to the nearest cent. Now notice when I did this, I went past a cent. That's 92 cents, and I went past that. But they want the final answer to be rounded to the nearest cent. If you're doing intermediate calculations, you need to carry more decimal places than the final result needs to be, or you might be off. So if they want the final answer to be rounded to the nearest cent, and I'm doing intermediate calculations like I did here, I'm going to take at least one extra decimal place. And the same thing down bottom. I want to change that now, and it's negative. Don't forget the sign. I want to change that by division. Take your calculator. 37 divided by 38 is 0.974, and remember it's negative. And remember they want it to the nearest cent, but if I'm doing an intermediate calculation, I'm going to take more than that. So I'll at least take 3. And now all I'll do is add them up. I add those two numbers up. That number's positive, that number's negative, so it's like subtraction. And when you finish subtracting, you get a negative. You get negative 0.053. Now we're ready to round it off to the nearest cent. The cent is here where the 5 is. That's the cent. And 3 is smaller than 5, so you round it just to 5. It doesn't go up. So to the nearest cent, the expected value of the bet is negative 5 cents. $0.05 is 5 cents. And negative just means it's a loss. So you're expected to lose. That game is not in your favor. If you did it over and over again, hundreds of times, you would lose on average. And you would lose a nickel each time you did it, on average. So think about how that was done. Your goal in all these problems is to eventually end up with a table of values and probabilities that you can operate on. Multiply and then add. So these expected values are averages. It's not what happens on any particular case, it's what happens on average. If you do something a bunch of times, what happens on average? Let's do another. This time we've got a lottery. It costs $2 to play this lottery. And the way it works is this. The player chooses a 3-digit number between 000 and 999. Notice there are 1,000 of them. If you started at 1 to 999, that'd be 999. By starting at 0, you've got 1,000 of them. And if the number's selected, whatever you chose, if it gets selected, you win $500. But it cost you $2 to play, so you really only net out $498. So even though you win $500, you had to pay $2 to buy your lottery ticket. And that money does not come back to you no matter what. And the question is, what is the expected value of this game to the nearest cent? This is exactly the same notion as we did in the previous problem, so let's just go to it. If you're betting, you can only win or lose. So let's look at the probability of winning. You're betting on a single 3-digit number, and as we said earlier, there are 1,000 of them. If you go from 1 to 999, that'd only be 999. By going from 0 to 999, you have 1,000 of them. There's only one winner, so you have a probability of 1/1000th of winning. It says you win 500, but you had to pay $2 for the ticket and you don't get that money back, so you really only net winning $498, and you need to think of it that way. So that's what happens when you win. And I'll put it into the table. My goal is always to get back to the table. The other possibility is I lose. If I lose the $2. I only lose the $2 it cost me to buy the lottery ticket. But if you have a 1 out of 1,000 chance of winning, that means you have a 999 out of 1,000 chance of losing. So you put that in your table, and don't forget that it's a $2 loss, so it's negative. And then again, just as before, you multiply. And when you get everything done, you want to add them together. So I left everything with a 1,000 denominator. That means I can just add, or in this case, subtract the numerators. So I can do 499 minus 1998, and that comes out to be negative 1,499 over 1,000. And if you divide that out, you get negative $1.50. Notice I did this a little bit differently than last time. Last time I took the division and made it to a decimal and then did the subtraction. This time I did the subtraction, leaving it as a fraction, and did the decimal at the end. You do have your choice. You can do it either way. But if you do it the other way and do the intermediate decimal values first, you want to take more decimal places than you actually need at the end. So that's one reason in this problem why it might be better to leave it as a fraction. But if you do go ahead and turn it to a decimal here and turn this into a decimal here, take at least 3 decimal places and then round it off to $1.50 at the end. And remember, it's negative $1.50. So the nearest cent, the expected value of this game is negative $1.50. That means it's not fair to you. In general, you're going to lose about $1.50 each time you play. If a game has an expected value of 0, we call that game fair. And the reason is obvious, because on average, a player is not going to win or lose. It's a fair game if on average you break even. But let's go back and look at the game we just did, that lottery ticket game, and see if we can find a ticket price that would make the game fair. If you set the price of the ticket right, you can make the game fair. And it's actually very easy to do. So here's the lottery problem, the same one we just solved. When we did all the work, we found out that the expected value of the game is negative 150. Here's the trick. All you have to do to make the game fair is adjust the cost of the ticket by the expected value. So if the cost of the ticket is $2, if you adjust it by taking $1.50 away from it, the result will be a fair game. So to make that game fair, I take the cost of the ticket and I adjust it by the expected value. And since the expected value is negative, it's like subtracting $1.50 from $2. So that means if I wanted this game to be fair, or the lottery to be fair, I would price the ticket at 50 cents. Now obviously someone trying to raise money in the lottery doesn't want to do that because they want to make a profit. If they sold a bunch of tickets at 50 cents each, by the time they paid off the winnings, they probably wouldn't have any profit. So that's why you're going to have a ticket cost that's well above the cost that would actually make the game fair.